All right, thank you very much. Thanks for having me, and good morning, afternoon, or evening to everyone that's joining. Like Eleftheria said, I'm actually very comfortable being interrupted, so don't hesitate to ask questions. I'll try to pause once every one or two slides just to make sure, to make sure we cover all the clarification questions. But more substantive discussion questions, I think it's better to keep for the Q&A part at the end. Cool. So the motivation is relatively simple. I think we all know that at this point, there's an increasing number of products and services that leverage customer data to learn and to improve those products and services. And although I guess learning from customers is not something new, so firms have been trying to learn from their customers for like at least a century. I think there's several things that have greatly accelerated this this process in the past, I don't know, 1 or 2 decades. The first one is obviously digitization of most products and services. So every product and service now at least has a digital component and a component that's in the cloud. And then second, of course, is just cheaper to store data, and firms have gotten, and we now have tools to better process data using artificial intelligence and machine learning algorithms. So as a result, so there are 3 things that are important, and they also actually matter for our paper. So the first one is that learning from customer data actually directly translates into improving the willingness to pay of products and services that learn from their customers. The second one is that the cycles of learning have gotten a lot faster. So whereas again, in the past, firms may have learned from their customers and eventually incorporated their learnings in the products, that process used to take a long time. So if you think, I'll take a silly example. Think about car manufacturers. Like Toyota would sell this model's Toyotas. They'll get some feedback from customers and they'll think, oh, maybe we should change this part of the design. And then the improvements will get incorporated in the next model of Toyota 5 years from now. Obviously, this is a lot faster today. So again, because of most products are digital, they can actually collect data and improve, and a lot of products contain software components. They can actually get improved, so they can learn and improve within the consumption lifetime of customers. So at this point, you buy a product, you actually expect the product to improve while you're consuming it. And I'm emphasizing this because it'll be important at one point in the model. And finally, the other piece that I think is quite new is that nowadays the improvements in the products and services can actually be customized to individual customers. So it's not just that the product improves for all customers at the same time, but some of the improvements are very specific to customers. And this leads us naturally to distinguish learning from customers that learnings that apply to all customers versus learnings that are customer specific. And like I said, there's lots of examples of this. I just want to emphasize this. We have one slide with varied examples here. I'm not going to go through all of them, but there are many, many more. And again, it used to be that most of the examples were very technical products. So you can think about Google Maps, Waze, or autonomous vehicle systems like Waymo, Mobileye, and others. But I think what's remarkable is that there's actually even the most mundane products today are acquiring the capability of, again, gathering customer data, learning from that customer data, and then, improving based on the data. One thing that I want to mention here, just, as you look through these examples, again, in some cases, the learning is truly mostly across customers. So we learn from all customers and the learnings are translated into improvements for everyone. So this would be something like, say, Google Maps. What really matters is, the more customers Google Maps has, well, they can get traffic, they can make better traffic predictions for everyone. In other cases, most of the learning is customized, i.e. it's specific to individual customers. So you can think of something like smart connected devices like thermostats, fridges, lots of other examples. Here, what really matters is not really how many customers are using the same product, but how much the same customers use the product. So if I have a smart thermostat, the more I use it, the better it becomes for me because it learns about my usage patterns. But it's not necessarily the case that it learns from other users. And then, of course, I would say in a lot of these examples, both of these things are true. So the learnings are both across customers, across users, and user specific. So this is true, I guess, for most of the other examples here. All right, so here are the main questions that, that we're interested in this paper. So in a world with data-enabled learning, what does competitive advantage look like? In particular, we're going to look at two firms. So we want to understand under what conditions and what determines competitive advantage when you have data-enabled learning. The second one is this distinction, which I've already alluded to, between learning learning across users and learning that is user specific. And it turns out once we get to the model, it is actually quite interesting to look at the differences between the two, because they'll have different implications for competitive advantage and firm profits. And then finally, the final question that we want to study is, what are the conditions under which data-enabled learning actually leads to network effects? And of course, implicit in this question is the notion that we don't believe that data-enabled learning is necessarily a network effect. By the way, some people actually do think that the two are pretty much synonymous, or in other words, as soon as you have data-enabled learning, you have this virtuous cycle. Well, at least once you have learning across users. So a lot of people believe if you have data-enabled learning across users, so the more users I have, the more I learn, and therefore the product gets better. You might say, okay, that's a virtuous cycle that looks very similar, in fact, maybe indistinguishable from network effects. I think it's important to be more precise here, and I'll spend some time on this question because I think it's important. Even if you think that's actually a network effect, the mere fact that the products learn the more users they have does not necessarily mean that you have the kind of coordination issues and chicken and egg problems that you would expect to have, and that are actually the hallmark of traditional network effects. You actually need something more in order to truly have network effects. So this would be the last part of the talk. Let me pause here to see if there are any burning questions.
Hensi by Isaac says that here learning is about a particular product.
I'm sorry?
Hensi says that here learning is about a particular product. Is there an equivalence if I am learning about new products and new product design and introduction?
No, I think So I think it's important to emphasize this. This is about a specific product. So it's given a product. There are two firms selling this product, or there's firms selling this product. What we mean, I think this is very important to be clear on. What we mean by data-enabled learning is within a product or service. A given product or service, a firm is selling that product to multiple users. Either the more users it has, the better it is able to improve the product over time, or the more I serve an individual user, I can improve the product over time for that particular user. It's not about new product introductions or learning across different products, which, by the way, can also be true, and I think it's very important in some context, but that's not what we're looking at.
Thanks.
Anything else?
I don't think so.
Okay, no problem. All right, so in terms of relationship with the previous literature, I mean, the first thing that should come to everyone's mind is, well, this sounds, at least at a very high level, related to the old literature on learning by doing. And it is true there are similarities, right? I mean, the big difference is, of course, we model data-enabled learning in our paper is about improving willingness to pay, versus in the learning by doing literature, so learning from data actually leads to decreases in cost. Now, if you strip our models to the most simplest possible version, it is true that there is a very clear mapping between improving willingness to pay or decreasing cost. But you'd have to take out learning within consumption lifetime. You'd have to abstract away from the within user learning that I talked about. And even then, we do actually get so even if you say, okay, well, there's a clear correspondence between what we're doing and traditional learning by doing literature, I think even then we actually have a few new results. So, we introduce vertical rather than just horizontal differentiation, and we get some interesting results regarding efficiency and consumer surplus. We're also actually, because our model turns out it's fully dynamic, but it turns out to be very tractable, we can get some very clear and very nice comparative statics on the learning function. But I would say most importantly, we're able to address, given our focus, we're able to address entirely new issues which haven't been addressed by the learning by doing literature. So in particular, we can talk about What is the impact of data sharing policies? We can make this very important distinction between across user and within user learning, and we can get to the issue of network effects. The other one, the other related strand of literature is on switching costs, and you can think in some case, so you can think of within user learning in our model as basically a form of endogenous switching costs. Like the more time I spend using a certain product, the more this product learns about me, and the more my utility from using this product, the higher the utility of using this product, therefore the less likely I am to switch to a different product. So I think it's a nice point to keep in mind. I don't think I've seen this in the switching cost literature to date. And then there are several more recent papers that are, at a high level related and that look at interesting issues related to data-enabled learning. I'm not going to go through detail. I mean, there's very clear differences between what we do and these papers. I mean, I think the focus in each of these papers is quite different. At a high level, what I think is fair to say is that ours is truly the first, the first model to explicitly incorporate firm pricing and consumer choices in a fully dynamic model with agents are forward-looking and data learning can accumulate over time. Unless there are any other questions, I'm going to start. I'm going to get into the model now.
You can go on.
Okay. Cool. So I'll start with so the baseline is going to be the model with across user learning. So there are two firms, an incumbent, you can think of them as being an incumbent and an entrant, and they're competing in prices over an infinite horizon. We're going to discount everything by factor delta and assume that both firms have the same marginal cost C and they compete in prices, so they set prices in every period. In every period, there's a continuum equal to measure 1 of identical consumers. Now, you can think of these in this model, in the cross-user learning model, you can think of these consumers as either being new consumers in every period, so consumers live one period, die, and there's a completely new cohort that comes next period, or it's the same consumers in every period, but they can costlessly switch products across period. So if they choose to buy from firm I this period, they can costlessly switch to firm E next period. So the model is going to it won't matter which of these interpretations we choose to go for. In this context with the cross-user learning, it will matter later when we introduce within user learning. So here's obviously the important part is how we specify utilities. So for each of the two firms, I or E, there's going to be a standalone utility, so standalone value denoted by SI, small si, and then there's going to be the learning part. So the learning part is given by a function fi, so we allow the two learning functions to be different for the two firms. And the only restriction that we impose basically on the learning function is that it's increasing. And if there's no previous, if a particular firm, firm I, has not served any customers in the past, then the value of its learning is equal to 0. So fi of 0 is equal to 0. So fi is going to depend on ni, which is total number of consumers that firm has served in the past. And we're also going to assume that there's a cap. So there's a maximum level of learning beyond which the firm cannot learn anymore. So past a certain number of total users served in the past, there's nothing left to learn, which I think is relatively realistic. So, it obviously depends on the industry, but it's relatively natural to assume this. Now, as it turns out, we can actually, the main results, we can relax this assumption and actually allow the learning function to be unbounded, so to increase indefinitely under certain technical assumptions, which are actually not very restrictive. So just to give you an example, again, the shape of the function, it turns out we can accommodate any shape of the learning functions. Can look something like this, or can be discontinuous as long as it's increasing. So in order to, the goal here obviously is to characterize the value function, so price discounted value of firm profits, and also we want to know which firm is going to win. So we're going to denote by VI and VE the two firm value functions, and obviously they will depend at a given point in time on the total number of users that each firm has served in the past, so NI and NE. So we start with a very easy case. So the easiest possible case is when both firms have maxed out their learning. So both firms have served enough customers that they've reached the maximum level of learning that each of them can reach. So at that point, from that point onwards, it's actually simple Bertrand competition over infinite periods with vertical differentiation. So the firm that has the highest standalone utility plus maximum value of its learning is going to win. So therefore you get these very simple expressions, right? So the condition for E to win is SI minus SE greater than FI NI bar minus FE of NE bar. And then the value functions are given by the two expressions that you see there. So it's very, very simple. Now, so we start with this. So this is basically the initial condition, and the analysis in the paper proceeds by backwards induction. In fact, it's going to be actually two-dimensional backwards induction because we have to vary both NI and NE. So what's going to happen when now we have NI and NE before the firms reach their thresholds? Well, if a firm hasn't reached its maximum learning threshold, it is naturally given infinite periods. Each firm is going to be willing to offer a subsidy which is equal to the difference in its future value if it wins the current period and therefore learns. And it's the willingness to pay it can offer is higher versus the case in which it loses in the current period and stays at the same learning value. We're going to skip obviously I'm going to skip the actual proof. Again, it's backwards induction, use it in 2 dimensions, and I'll show you directly the main result, the first main result. So this proposition characterizes the conditions under which E wins, so firm E or firm I wins. And so let me just state the main result. There exists a unique Markov perfect equilibrium given NI and NE in which E wins all periods starting from today, if and only if SI minus SE is greater than this threshold delta, and delta has the expression that you see there. So the first thing to note is that either E wins all periods or I wins all periods. This is not very surprising given that it's basically Bertrand composition. Second thing, if you look at the threshold delta of NI and NE, you can think of it as essentially capturing I's competitive advantage. Why? Because basically if delta is higher, then that requires the difference in standalone values SI minus E minus SE minus SI to be higher. So therefore it makes it harder for E to win. And again, not surprisingly, delta of NI of NE is actually increasing in NI and decreasing in NE. So the more consumers firm I has served in the past, the higher I's competitive advantage, and the more difficult it is for E to win. And vice versa, when firm E had more consumers in the past. Second thing to note, if you look actually a little bit more closely at the threshold, so the expression of the threshold delta, you actually notice if you divide it by 1 minus delta, it's actually pretty simple. So what it is, it's basically the present discounted value of the future value of learning for firm I, assuming that I wins in every period. So it increases, every period I gains 1 more unit of learning, minus the same thing, present discounted value of future learning for firm E, assuming E wins in every period. So actually what this means, so given this proportionality, what this actually means is that basically firm E wins if and only if the present discounted value of its future learning over the winning path is higher than what firm I can offer. In other words, the equilibrium outcome is efficient. So I'll come back to this because it's actually a little bit more, it's not as obvious as it may look here. And then finally, the other thing that I actually mentioned before, the results here in the proof were obtained with assuming these maximum levels of learning for both firms. But it turns out the results actually also hold when we take NI bar and NE bar and let them go to infinity, i.e. we allow the two learning functions to be unbounded. So the only requirement there is that the learning functions must be bounded by some power function in the limit. So we can actually accommodate linear learning for both firms that increase indefinitely. And you will get the same equilibrium characterization still works. Any questions?
Okay. We have a question from Yossi Spiegel saying, why does the rival without sales stay in the market? In fact, if firms have fixed cost, the loser will exit, and maybe even before the last period, when its chances to be eventually winner go below some threshold.
So I think that's a fair question. Again, the model is relatively simple. So you can actually introduce some uncertainty in this model, and you will get. So in this case, it is true again. If the same firm will win, so we know in this period, if firm E wins this period, it's going to win in all future periods. Of course, in reality, it's not quite like this. If you introduce some uncertainty, you may get something like it's possible for firm E to win for a couple periods, and then eventually for firm I to win in the long run. We don't have that in the model, but you know it is. I think that's the interpretation to have in mind.
Yeah.
Anything else?
Nope, for now.
Okay, so one more thing that I wanted to mention here, again, sort of in the spirit of previewing a bit the network effect story that I'll talk about, you may notice that, so you may ask, so here what's happening is, even though, so consumers are forward-looking, they're not myopic, they're actually forward-looking. However, there's no coordination issue. So in the following sense, consumers actually don't have to form expectations about what's going to happen in the future in this analysis for this case. And the reason is the following, like I mentioned earlier, because it's costless for consumers to switch from one period to the next, and because each consumer is atomless, so the decision of a consumer to choose one firm or the other is not going to materially impact the outcome of the competition game. So therefore, the consumer, the only thing they care about is, I'm just going to look at today's utilities, so standalone utility plus learning value for each of the two firms. I'm going to choose the one that offers the higher value. The consumer knows that there's going to be utility in the future, but the point is they don't have to care about that in every single period. So they make decisions period by period without looking into the future. So that means there's no reason to have, there are no coordination issues here. So a consumer doesn't have to worry about, well, how many other consumers are going to choose the same firm as I do. That's going to change when we introduce within user learning. And that's actually leads to a very nice way in which you can obtain network effects by combining the two types of learning. I just wanted to preview it here because, you know, some people in the past have had questions about how come, you know, the analysis here seems kind of deceptively simple because there's no coordination issues. There's no expectations. And this is the explanation for that. Okay, so a few more things that we can say about the equilibrium with the cross-user learning. So an interesting thing here is basically there's actually 4 regions. So we can take a closer look at the pricing of the two firms. So given the two firms as symmetric, I'm just going to focus on the first two. So conditional on firm I winning, there are basically 2 regions. If the standalone utility of firm E, so the first bullet point, SE minus SI, is very small, in that case, I is going to win in every period, and E is not even going to try to. This is probably related to the previous question. Why does E stay in the market? In this case, basically, I has such an advantage that E is not even going to try to subsidize. So it's going to price at cost in all periods. If, on the other hand, SE minus SI has this intermediate value between delta of NI, NE plus 1, and delta of NI and NE, in that case, E is actually willing to offer a subsidy, at least in the current period. And the idea is E is going to subsidize because if by chance, by subsidizing, it ends up winning the current period, again, you can introduce some like random parameter or some uncertainty, and somehow if E turns out to win this current period, the equilibrium flips and E is actually is going to win all future periods, which actually has an interesting consequence. So there's basically 3 possibilities. So I'm going to show them here. If the losing firm has very low standalone value, like I said, the losing firm basically gives up right away and essentially prices at cost indefinitely. If, on the other hand, the two firms are relatively close in standalone value, sufficiently close in standalone value, it is possible that the losing firm will offer a subsidy indefinitely in the hope of winning. So again, this also provides an answer as to why the firm, the firm that's losing may actually still stay in the market, because there's this like ever-present hope of winning. So if the losing firm was to win one period, it will win everything thereafter. So again, if you introduce some small uncertainty, that is possible, and that justifies the losing firm staying in the market. And of course, there's the middle case, and there's a parameter range for that, in which the losing firm offers a subsidy for the first K periods, after which it basically gives up. Perhaps even more surprisingly, it is possible that the winning firm also subsidizes for a limited number of periods. So the idea is, if the winning firm, so there's a firm that has a long run advantage, and eventually it should end up winning. However, based on current learnings, that firm is behind. Well, in that case, the winning firm will have to subsidize at least the current period in order to basically win, to get its learning higher and beat the other firm. Another interesting question, and this is there's a very clear parallel between this and the traditional learning by doing literature. So you can ask the question: are the firms better off or worse off? Are they made better off or worse off by the prospect of future learning? So in other words, what is the effect of the possibility of future learning on firm profits? So it turns out there's two cases. Well, actually, short answer is it can go both ways depending on the learning functions. So in particular, if the learning functions are symmetric, so if the firms are perfectly symmetric, so they have the same learning functions and they start from the exact same amount of learning, so NI equal to NE, it turns out that the present discounted value of profits of the winning firm is actually higher when there's future learning than when there's no future learning. And the reason for that is because if we take away all the asymmetries between the two firms, basically learning provides endogenous scope for vertical differentiation. So the winning firm is going to end up accumulating learning, which actually makes it, so if there is future learning, basically there's scope for the firm that's going to eventually win to get more vertically differentiated from its rival, and that actually relaxes competition. On the other hand, if the two firms' learning functions are asymmetric, and the SI and SE is sufficiently close to the boundary delta NI and NE, then it turns out the PDV of joint profits is actually lower with learning than if there's no scope for future learning. So this is the flip side. It basically illustrates that there's a competing force, which was actually identified in the previous learning by doing literature. And here the idea is that future learning actually, the fact that there's future learning to be had makes firms price more aggressively. So they're more willing to subsidize in order to, to gain the learning and improve their willingness to pay. So in general, there are these two competing forces, and it could go either way. I guess our contribution here is to show that is to actually emphasize that first aspect, the vertical differentiation piece, which is not present in the learning by doing literature. All right, so the other thing that I want to talk about here in the context of cross-user learning is the efficiency result. So let me state it here as a proposition. So the unique Markov perfect equilibrium outcome that I've shown you earlier is actually socially optimal. Now, again, this may seem, on first glance, you may think, oh, that actually kind of makes sense. So consumers are short-sighted. Again, they're not myopic. They're completely rational, but they, again, like I said earlier, they don't have to worry about the future. So consumers only have to worry about the willingness to pay offered by each firm, so the utility offered by each firm today, because they can costlessly switch. So in some sense, well, yeah, the consumers are short-sighted because they only care about the utility today, but the firms, are willing to subsidize in the current period the entire present discounted value of future profit if they end up winning. So at some level, you might think, okay, well, that basically suggests whichever firm offers higher present discounted value of profits should actually win. So you may, in some sense, you may expect a social efficiency result. It turns out it's actually not as obvious. And the reason is the following. You have to realize the winning firm is not going to extract. So in every period, the winning firm only extracts the PDV of surplus that it creates in addition, so above the losing firm. So at least in principle, there's no reason that actually should lead to social efficiency. And in fact, we show that this intuition is actually pretty, like in some sense, misleading, and it's confirmed by looking at a finite period model, a version of our model. And it turns out the social efficiency result is actually not true with finite periods. So it's actually quite interesting. With finite periods, the outcome, so whichever firm wins, is not in general socially optimal. However, when you take the number of periods and make it go to infinity, the inefficiency disappears, and you get the result that I mentioned earlier, i.e. that the outcome is socially optimal, which is, again, it's actually quite remarkable. And then finally, you can also look at consumer surplus, and because the winning firm only offers the surplus that only has to match the surplus offered by the losing firm, it turns out that learning by the winning firm actually weakly decreases consumer surplus. And the reason is very simple. Either the losing firm was pricing at cost anyway, so more learning by the winning firm has no impact on consumer surplus because that just means the losing firm offers the exact same surplus, or more learning by the winning firm makes the losing firm go from offering a subsidy to giving up earlier, which means it offers less subsidy to consumers. So actually consumer surplus is being decreased when the winning firm learns more. And this provides a very natural transition to the next question. Well, if you worry about consumer surplus, and if it is true that learning by the winning firm hurts consumer surplus, well, one might consider a data sharing policy, which would require the winning firm to share its learnings with the losing firm in order to keep firms competitive and basically keep competitive pressure on the winning firm, and therefore help consumer surplus. So what we show, I'm not going to show you the details. That we analyze this question using a variant of the model, actually special case of the model. But it turns out that this intuition that data sharing actually helps consumer surplus is actually incorrect, and that it's incomplete. So there's a downside to a policy that requires data sharing. The problem, if you require the winning firm I to share its data with firm E, yes, you put more competitive pressure on I, but you also reduce firm E's incentive to offer a subsidy when the data sharing is anticipated. Again, the only reason firm E is going to engage in subsidies is because it needs to fight in order to win. If it knows that it's going to get data and learning no matter what, so whether it wins or whether it loses, it has a reduced incentive to subsidize, and therefore overall it's unclear that data sharing actually helps consumer surplus. So we actually show this trade-off formally. So in the very simple, we actually take the simplest possible version of our model to produce this trade-off, and we show that if in equilibrium E no longer offers a subsidy as a result of the data sharing policy, then actually consumer surplus can be lower with data sharing than without any data sharing. If there are any questions?
We're gonna keep the question for the Q&A that we have already here.
Okay, cool. I just want to pause at intervals to make sure there's no clarification issues. All right, so now I'm going to move to the next part, which is within user learning. So up to here, it was again, learning was across users. Now we're going to look at a very similar model, a similar version of the model, focused on within user learning. So it's the same two firms, I and E, they're competing over infinitely many periods of time. There's a continuum of n equal 1, but now it has to be the same consumers in every period. So the consumers are infinitely lived, and they have to be the same ones in every period in order to meaningfully talk about within user learning. So the learning functions are the same. So we're going to keep everything the same just for the purposes of comparisons, but of course the interpretation is different here. So NI now means the total number of times a given consumer has purchased from firm I. So there's no longer any scope for cross-user learning. The only thing that matters is how many times has a consumer bought from firm I in the past. And to make things simpler and to keep things streamlined, we're going to assume that firms can price discriminate based on a consumer's history of purchases. I think that's also somewhat realistic. Firms routinely make offers to to consumers that have been with them for a longer period of time or for shorter periods of time, essentially based on the amount of times those consumers have purchased from them. And this enables us basically to simplify this model to one in which basically there's one representative consumer in the case of within user learning. But again, the learning, just the only thing to emphasize here, everything is pretty much the same as in the across user learning model. The only thing to remember, so the learning functions are the same. There's a standalone value, and then there's an increasing piece of the learning function. Of course, the interpretation is different. So we'll just give you the main results very quickly. Actually, maybe one thing to emphasize here, even though it looks very similar, the proofs are actually quite different. So yeah, I'm skipping the proofs, but the logic of the proof is different. So we get, again, there's a unique Markov perfect equilibrium in which E wins if and only if the same condition as with the cross-user learning holds. So the condition is SI minus SE is greater than delta of NI and NE. And the delta is the exact same threshold that we had with the cross-user learning. And once again, for the same reasons, the equilibrium outcome is socially optimal. So first thing to note, same thresholds, but here, actually, the logic for social optimality is a lot more straightforward. So I would say it's not surprising. And the reason is these consumers, so within user learning, consumers now have to be forward-looking. So this was very different from the case with across user learning, where they only have to care about current utility. If there's within user learning, well, each user will actually have to, when deciding today which firm to go for, will actually have to think about, well, which firm is going to learn more and faster in the future if I go with them? Because obviously, once I go with one firm, I'm going to essentially commit and increase my switching cost by increasing the learning that I have with that firm. So naturally, consumers are going to choose the firm that can offer more learning in the future. So in some sense, it's actually easier to understand why the equilibrium is socially optimal. If one firm offers more future learning, so in terms of present discounted values, if one firm offers more future learning than the other, that firm should win, given Bertrand competition. And in fact, to underscore this, even if you remove pricing, so if you assume that the two firms have prices equal to 0 in every period, so maybe and that's actually true for a lot of products and services are priced at 0, you still get the same outcome for the reason that I just mentioned. So pricing here is actually not the main driver of the result. What really matters here is the fact that consumers are forward-looking. By the way, this is in stark contrast with the case with the cross-user learning, where everything was driven by pricing. Again, you get the subsidies and everything. So if we remove pricing, we're not going to get the socially efficient outcome. Now, the other interesting question, this is sort of the main part here is the comparison between within user learning and across user learning. So what we want to know is naturally, even though the threshold for which firm wins is the same, what about firm profits? And it turns out, if you focus on the third bullet point in proposition 9, it turns out that the present discounted value of the winning firm is actually strictly lower in the case of within user learning than in the case with across user learning. And the reason for that is the following. When we have within user learning, consumers are forward looking and they actually have to be compensated. So they understand the fact that if they go with the winning firm in this period, you gotta remember, learning by the winning firm actually hurts consumers. So because the consumers are forward looking, they will actually have to be compensated in the price that they're being offered today for making the winning firm stronger the next period, and therefore basically having lower utility. So this mechanism is not present in the case with a cross-user learning, because again, the case with a cross-user learning, consumers effectively only look at the current period. So as a result, price competition is actually more intense within user learning than with a cross-user learning, and that explains why the equilibrium profits of the winning firm is lower within user learning. And conversely, obviously, consumers are better off in the case of within user learning. And in fact, we can conduct the same exercise looking at the data sharing policy. So if you look at data sharing, actually data sharing is more likely to lower consumer surplus in the case of within user learning, because we already have more competition between the two firms in the case of within user learning relative to across user learning. Any questions?
Can I see it like compensating the consumers for giving their information in a sense?
Say that again?
Can I see it as compensating the consumers for giving the information about themselves?
Sure, you can compensate them, but who would compensate them?
This thing that you say that consumers must be compensated.
No, sorry. That must be compensated. So I don't mean like actually. So this is a metaphor. It's what I'm trying to say here is that the pricing of the firms. So this is like endogenous in the model. So the firms are competing. Mm-hmm. So if I want to win, what I mean is compensated like implicitly by the prices offered by the firms, right? So there's price competition, and then one of the firms, if I want to win, and consumers are forward-looking, I have to basically lower my price in order to win them, because they understand, hold on, if we come with you, we're going to make you stronger because you're going to learn and you're going to be in a stronger position next period, and therefore you're going to be able to actually, extract more surplus from us. We understand this, and therefore you have to offer us a better price if you actually want us to come with you. But it's not like compensation as in like, compensate me for that. It's like, it's a metaphor for like what's going on endogenously with the pricing. That's what I meant. So I should have put compensated in between quotation marks. All right, so if there are no questions, I'll get to the last part, so the third part, which is about network effects and beliefs. So again, this is the part I think is very interesting given the current debates about data. So a lot of people think that as soon as you have data-enabled learning, you have network effects. I think I don't have a strong view, although I prefer to reserve the term network effects for like true network effects. But you can see why, right? I mean, if you have data-enabled learning, you have this virtuous cycle. More consumers means more data, means better product, means more consumers, right? So that looks very, very similar to network effects. Now, I think this should be very clear based on the model that I've shown you so far, that this sort of like superficial similarity actually breaks down in one very important aspect. So so I'm fine actually calling that a network effect. The issue is up to now, so in the two models, across user learning and within user learning that I've shown you, even if you say, okay, those are network effects, well, those network effects have not created any coordination problem, the kind that you normally see with traditional network effects. So in the case with the cross-user learning, like I said, no consumer has to worry about, well, how many other consumers are going to adopt the same firm? And the reason is, well, they can costlessly switch across periods. So they don't care actually if the other consumers go with the same firm in the current period or with the other firm. So there's no coordination issue. And of course, within user learning, I don't care at all about other consumers. The only thing that matters is how many times I use the same firm. So up to now, there's been no scope like for network effects to play any role in the equilibrium analysis. Now, we can actually introduce, so this actually makes it very clear how you can introduce network effects, how you can have data-enabled learning generate true network effects by having some sort of consumer coordination problems. And you can do that in two ways, and we do that in the paper, in two main ways. The first one, and I think that's sort of the easiest one to understand. So first of all, you have to have a cross-user learning, right? If all you have is within user learning, you're never going to get network effects because, well, consumers don't care at all. Like there's no value to an individual consumer of other consumers consuming the same product. So you have to have, in the first place, you have to have a cross-user learning. But that by itself, like I said, is not enough. So the first way in which you can generate true network effects is to combine across user learning with learning within the consumption lifetime. So like I said, one of the key things that has been happening or been accelerating over the past decade is that now products, especially software products, actually learn and improve within the consumption lifetime. So there's a very easy way to take our model. So the first very easy way to generate network effects in our model is to take the first model with the cross-user learning and then assume that the current current willingness to pay of a consumer in the current period is standalone value of past, so value of learning from previous consumers, but also value of learning from all current consumers. So basically, I'm going to allow the product to improve within the current period. If that's the case, well, immediately each consumer now is going to have to think about, okay, what is the value that I get from this product? It also depends on how many other consumers are going to adopt the same product today in the same period as I do. So that's almost like you're exogenously introducing the network effect by assuming this within period learning. Similar, but a little bit more subtle, no within period learning, but let's assume now that when consumers buy a product, they pay the price once, and once they buy a product, they only have to pay the price once, and then they can consume that product for several periods, could be infinite periods, without having to pay again. Here, basically, once we do that, what we're essentially introducing is an endogenous switching cost due to price. So if I'm a consumer, I choose one of the two firms in the current period. Well, in the next period, yes, I can switch to the other firm, but the problem is I have to pay their price. Versus if I stick to my current firm, I'm actually, I don't have to pay the price again. By doing that, you have an endogenous switching cost, and now you combine that with a cross-user learning. We have once again a network effect because the consumer now has to consider, well, if I'm gonna go with this firm, I'm gonna be stuck with them for a while because it's harder for me to switch to the other firm, and therefore now I actually have to calculate, well, how many other consumers are going to go with the same firm because that impacts my future value of learning. So that's the first way to do it. I would say, so I'm not gonna show you the models that correspond to this. We have them in the paper. We think this one, so the second one is actually more the most interesting way, and perhaps a little bit, it's not obvious, and it's relatively elegant. So another way to generate true network effects with coordination problems is simply combining the two models that I've shown you before. So across user learning and within user learning. So here the logic is the following. Within user learning creates an endogenous switching cost for consumers. So if I'm a consumer, again, now I have to think, well, if I go with this firm, I'm going to accumulate learning with them, so it's going to make it harder and harder for me, or more costly to switch to the other firm. And then because it's hard to switch to the other firm, I better make sure in this period that I choose the firm that also has the most number of users, that will have the most number of users in the future, because I also benefit from across user learning. So it's actually quite nice. I mean, if caring about within user learning gives you the endogenous switching cost, and then caring about across user learning gives you the full network effect. And you actually, in that case, we do have a coordination problem. So one application of this is, I mean, probably the easiest way to think about it is think about Google search. So people have asked this question to Halvarian and Google for a long time. Should we think about Google learning from consumers and getting better? Should we think of that as a network effect? And I think Halvarian's answer is always, well, no, it's not a network effect. That's just, learning by doing. So I think that's true, but basically based on this model, I think there's definitely a network effect. And the reason is, if you use Google, if you accept the fact that using Google more creates an endogenous switching cost because Google learns your preferences, understands what you're searching for, and it's just better, easier to use for you individually. And at the same time, Google also learns across users, which is also true. Well, then you do have a network effect. And I'm actually going to show you the model, like a brief version of the model that corresponds to this case. But long story short here, if we introduce one of these, so if we do one of these two things, so either across user learning plus learning within consumption lifetime, or across user and within user learning, basically now we actually have true network effects. So in this case, there's a consumer coordination problem. So there's a scope to introduce consumer beliefs in determining which firm wins. So this now becomes very, very similar, in fact, indistinguishable from the traditional analysis that we're all familiar with network effects, in which you have to actually specify beliefs, and you may have multiple equilibria depending on what those beliefs are. So I'll show you because I think it's interesting. Sorry.
I'm gonna interrupt you. Martin has a clarification question.
Yes.
So I think this the setting you were mentioning about the pure cross-user learning and these multiple periods of consumption. In a sense, what you're saying then is that the presence of true network effects depends on the pricing strategies available to the firm. In the sense
That's
that,
right.
So if I have this kind of buying, as you're mentioning, then it's satisfied. Whereas if I'm more of a rental agreement, then it's not satisfied.
That's right. That's right. Exactly. That's right. So if it's something, I think you're right. So in this case, you're right. It depends on the, right. So there's some products or services that you buy upfront, like, you know, I pay once and that's it. Or there are other products for which you pay either rental or maybe a subscription fee, right? So yeah, so essentially you would have to have something that commits you in terms of pricing, like you pay one price and you consume for several periods. As soon as you have that, basically that creates some sort of like endogenous switching cost due to pricing.
So I think I understand it, but of course it's often we think network effects is something which describes the features of a market, but here we see it depends on the type of pricing strategies.
Right, exactly. I think it's, so that's an interesting point. So it's basically, I think it's a little bit more than the traditional, you know, the pecuniary versus non-pecuniary network effect. So like, you know, I buy the stuff and therefore I get a bigger discount. So that's why, by the way, that's why I like, so both Julian and I, we prefer the second point, right? Where basically it doesn't depend on pricing at all. You generate network effect by within user learning and across user learning. I'm with you that this network effect that basically just depends on the nature of the pricing. Again, that's why I'm always very reluctant. Like I certainly don't think like data-enabled learning is the same as, you know, traditional network effects. Precisely for the reason that you mentioned, a lot of the cases actually it depends on the nature of prices. And in fact, what's cool about the second point, so the second point being across user and within user learning, we actually remove pricing altogether. So just to prove that you can get the network effects and it has nothing to do with prices, we put the I'll show you in the model actually here. This is where I was going. There's going to be no prices, so the two goods are priced at zero. Anything else?
Not for now.
Cool. All right, so let me briefly show you how this works. So across user and within user learning, again, same, so continuum of identical and infinitely lived consumers, and they can still costlessly switch between the two firms. So that's why there's no exogenous switching cost here. And we're gonna assume it's exactly what I just mentioned to Martin. The firm's price at zero in all periods, again, just to show that this is not like some sort of pecuniary network effect. And now what we're going to do is basically combine the two learning functions that I show you that previously we had separate. So a consumer that has previously consumed a small NI times from firm I, when that firm has served big NI consumers, is going to derive utility, which is standalone utility, plus a term FA, which is, I guess, learning from across user learning, plus a term FW, which is learning within users. So there's, you know, I'm basically combining the two components from before. And like I mentioned, within user learning creates here the endogenous switching cost comes from the within user learning. So again, there's nothing to do with prices. And the equilibrium is going to be pinned down by two deviations for consumers, the two best deviations for consumers. Every consumer can switch, so a consumer can switch to the other firm in all periods. So I have to compare, consumers are forward-looking, so I have to compare PDV, present discounted value of utility from offered by each of the two firms. But I also have another strategy, which is I'm going to go with the firm that offers the most the most utility from within user learning today, in order to, and then I can switch later in order to free ride on the across user learning that happens from the other users. So anyway, this is actually not that important. I'm just going to show you I mean, it's important for the analysis, but not for showing you the main result. So this is what the result looks like. Suppose both firms start with no previous learning. So they both start with blank slates both types of learning. So there's no across user learning, no previous across user learning, no previous within user learning for every consumer. So again, just like for those of you who are, hopefully most of you are familiar with the literature on network effects, you have to specify beliefs. And what we do here, we just compare two very widely used types of beliefs. Pareto beliefs, which basically says consumers are going to coordinate on the equilibrium that's best for them. So these beliefs, you can think of them as being symmetric. Like these beliefs don't favor any firm over the other. And then we're going to contrast that with beliefs that favor firm I as the incumbent. So that means consumers always coordinate on the equilibrium with adoption for firm I whenever that equilibrium exists. So what we want to show here is that, well, network effects do lead to a coordination problem, which means that beliefs matter. So with Pareto beliefs, given that the two firms are symmetric and they start with blank slates of learning, not surprisingly, the equilibrium is determined by whichever firm has higher standalone value. So SI minus SE is a greater than 0 or smaller than 0. That's socially optimal. If, on the other hand, beliefs favor firm I, the equilibrium is not going to be socially optimal. So it's going to be actually, of course, harder for firm E to win. So here the threshold has the expression that you can see there. And I think, again, details don't matter. I think the only thing to note from that expression, makes it very clear, is that the expression on the right-hand side of that condition, SE minus SI greater than delta times that min term, you need both types of learning in order for this network effect to actually make a difference between the two types of beliefs. So for example, if either the function FA is equal to 0 or the function FW is equal to 0, then the outcome with beliefs favorable to I would be exactly the same as the outcome with Pareto belief. So again, there will be no difference in the outcome, so network effects don't have any material impact. But of course, when you do, so this underscores the idea that in order to have network effects here, you need both types of learning. And they play slightly different roles, right? Within user learning creates endogenous switching cost, and across user learning means there's an interdependence of adoption decisions across consumers. All right, so I've reached a conclusion. I mean, I think what I want to emphasize is that this sort of data-enabled learning is truly becoming is completely widespread. It's not just tech products, it's pretty much any kind of product and service, even the most mundane ones, are acquiring the capability of having data, tracking user data, and learning and improving their products based on that data. Key determinants of competitive of outcomes with data-enabled learning. Again, profits are higher. Like this is the key comparison between across user learning and within user learning. Within user learning leads to more intense competition. I haven't really talked about this, but we have it in the paper. We can do some like very nice comparative statics in the learning functions. So very briefly, a firm's advantage is increasing in the learning in the learning curve, in the position that that firm has on the learning curve, and of course in the remaining learning potential. And then finally, so favorable user expectations create competitive advantage. So if I'm a firm and if there are true network effects, either because there's a cross-user learning and continued product improvement during consumption period, or within user learning, then you get true network effects, and then you can get the scope for consumer beliefs to add an additional layer of competitive advantage to whichever firm is favored by those beliefs. And that's it.